All right, welcome back to the second half of day 94. Hopefully you've already attempted all of these questions. If you haven't, please try each of them and then you can skim forward to the video. You don't want to do them as I'm doing them. You really don't learn much that way. You need to try first. So let's get to it. The first two questions are calculator active. The last two are no calculator. And I'm going to try to be as efficient as possible. The first one seems scary and is actually the easiest one on here. So we have a tank sitting on the ground, and I can draw a tank, I guess, if you want. The area in square feet of a horizontal cross section is blah, 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 blah. Now, they call this f of h. I don't really like that because they told us this is the area of a cross section. This function right here is our area function. They're telling us that if we have some sort of, I don't know, base, crazy whatever base on the ground, every single cross section, and it doesn't matter what the cross section is, let's pretend the cross section is a rectangle. Every cross section that's coming up out of here, wherever this might be, they're telling us we can find the area of the cross section using this function. That's really useful because they've skipped ahead. They want us to find the volume of the tank. Well, if we already have the area function and we want the volume of a single cross section, just adding in this little extra piece here, right? And this is going to be dh down here, everything's in terms of h, is just going to be the area function times dh, or if we wrote this out, 50.3 over e to the 0.2 h plus h times dh. That's how you find the volume of one of these whatever cross sections are. I don't know what they are. They didn't tell us that. It doesn't matter what that is. So if we want to find the actual volume here, we're just going to integrate. Right? We're going to integrate this little piece here, 50.3 e to the 0.2 h plus h times dh from what to what? Well, they said it's sitting on the ground, has a height of 10 feet. And they're telling us the area of the horizontal cross section. So I actually probably did a poor job. This should really be turning sideways, which I can't do here. But maybe we'll pretend this is my height axis going this way. That's a little silly, but that's okay. And 0 on the height axis is here and 10 is up here, right? And picture these coming off sideways then. So what they're telling us is that each of these h's, we can find this. So that means we're starting at 0. We're going to, not h, all the way up to 10. Okay, let's plug this into our calculator and call it good. So 50.3 e to the 0.2 h plus h, I only have to look at that 17 times, we should be fine. So menu, calculus, integral, we're going from 0 up to 10, easy enough, and it was some sort of fraction, and it was like 50.3. I'll fix this when I inevitably screw it up later on, and it's going to be e to the, nope, that's natural log, second try, e to the, and it was 0.2. I normally use x, but let's use h. Let's be creative here. H, right? And then it was like plus h squared dh. I'm certainly not going to hit enter because I'm sure I screwed something up here, so let's find it out. It's not h squared, it's just h. Alright, good thing I checked. So we're coming back here, we're going to delete that, and we should be good. Hit enter, and it gave us a weird error here, an approximate arithmetic. It usually does that when you end up with e's in here, because e is already an approximation, and if it can't find the antiderivative, it struggles. But 101.325, if you want more decimal places, I've highlighted too much, highlight, hit enter, 101.3253, and we're set. 101.3253, cool, go us. Remember on this, you need to have a setup and an answer. Usually a problem like this would be worth 3 points on a free response. I'd give you 2 points for the setup, 1 point for the answer. Might be 2 points, but it's probably 3. Alright, second one. Let R be the region enclosed by some sort of weird curvy graph here that we've called f of x, and the line y equals 4. Lovely. Okay, for each cross section perpendicular to x, isosceles right triangle with a leg in R. This is really similar to one of the examples we did today. Fancy that. So we have an isosceles right triangle where these two are the same. Okay, and if I want to write the area of that isosceles right triangle we talked earlier about, it's just 1/2 the base times the height, but because the base and the height are the same, we can just say it's the base squared. To find the base, though, it's going to be the top function, which is 4, minus the bottom function, which is this craziness right here, but I'm just going to write f of x. That seems to be easier. Okay, and then our volume function, we just do times dx, because that's going to give us a little bit of width here, nothing terrible. So then let's skip straight to our integral. We need to integrate this 1/2 parentheses 4 minus f of x squared dx from what to what? Well, they definitely cross at 0, it seems like. And then the second intersection point, that's our calculator active part. I think you'll even find if you set 4 equal to this equation over here, you'll really struggle solving for x. So x to the 4th minus 2.3x cubed plus 4, 0% chance I'm remembering that. So we have x to the 4th minus 2.3, I'm going to say x cubed, but with an actual cube, and then plus 4, x to the 4th, 2.3x. Oh, I crushed it. All right, it's a good evening. So we have this one, and then we have 4. We've done it, and we need to, of course, find their intersection point. So intersection-wise, menu, calculus, or I'm sorry, analyze graph, intersection. I'm going to click somewhere in the middle this time, which is going to be a tough one over here. There we go. It's going to be here. And then here, we found my intersection. It says 2.3 comma 4, but I'm never going to trust that. I bet there are more decimal places. So I hit plus. Oh, there aren't anymore. It's exactly 2.3. That's pretty shocking, honestly. Okay, so it intersects at 2.3. So this is the point 2.3 comma 4, so 0 to 2.3. And from here, we just hit enter, and I think we should be good. So let's get back to it. We have this. We're going to go, okay, I'm done with that. Menu, calculus, integral. We're going from 0 to 2.3, and then here's where we'll be clever. Instead of 1/2, 0.5, just so I don't have to do a fraction. 4 minus, and I didn't define the function, but remember, I graphed this function, and I'm pretty sure I graphed it in f1 of x. Okay, we don't want to forget our friendly square here. And then dx, 1/2 of top minus bottom squared, 1/2 base times height, 0 to 2.3. There we go, 3.5737. 3.5737. And of course, you only need to go 3 decimal places. I always go 1 further, just so you don't have to worry about rounding. You've got everything there, nothing too bad. So 2 down. Oh, nope, not 2 down, because we have a second piece. Oh, they really like this question too. It's so worth asking. So a vertical line x equals k divides the region R into, into 2 regions with equal areas. Write but do not solve an equation involving integral expressions whose solution gives the value of k. All right, well, let's at least draw a picture first. They're saying that we're going to be able to draw some line that's going to split R into 2 equal pieces. Let's say it's about here. No, okay. Let's say it's here. I just don't want you falling into the false assumption that this is just halfway between the line, that this is at 2. It's probably not at 2, but it's there-ish. Sounds good. This is the line x equals k. Well, there's 2 ways to do this, but no matter what, we're at least going to have to figure out how do we find the whole area of R. But that one's not too bad. The whole area of R, so R's area, is just going to be the integral from 0 to 2.3 of the top function minus the bottom function. That is the whole area. Cool. Now there's 2 things you can do here. Option 1, and either of these are fine, it's totally up to you. So let's just do it this way, and we'll split this in 2 ways. So option 1 is you can just go a little bit literal. You can say that we want our integral expression to be equal to half of the whole area. So this is my whole area. I just did that. And I know that if I integrate from 0 to k, and I should have done 0 over here, sorry. If I go from 0 to k, that answer of, again, doing top minus bottom should be equal to half of the whole area. And that would be an equation where we could actually go through, take the antiderivative, plug in k, solve for k, and it would tell us the x value that got us halfway through the area. The other option is we could say, well, if we know from 0 to k gives us half of the area, then we know from k to 2.3 will give us the other half of the area. These two are each half of the area, which means they have to be equal to each other. So either one of these are acceptable. I see them pretty equivalently amongst my students. It's totally up to you. All right, question 3. Wow, we've seen this region a lot. It's slightly different. This one's no calculator, square root of x. First step is find the area of R. Now, we've done problems like this before. I'll do this one in red. I'll do this one in green. And we've said that there are two options. Option 1 is we do the area of the red region first, and then we do the area of the green region second, and then we add them together. However, the other option is we could go right minus left all the way through, and I'm cheating a little bit here. I've already looked down. Part B says perpendicular to the y-axis. Perpendicular to the y-axis is this way, which means we're going to need a right minus left anyways, so let's just get ahead of the game. So we know a couple things. We first know that y equals the square root of x, and that means then if you square both sides that x equals y squared. We also know that y equals 6 minus x, which means if you add x and subtract y, you get x equals 6 minus y. So I'm going to use a right minus left to find the area. And we actually have to find the area without a calculator here. So here we go. We are going to integrate, and we're going right minus left. Remember, we're doing x values this time, and the bigger x value is always on the right. So my right function is 6 minus y, and my left function is going to be y squared. And we are integrating from 0, that's the bottom y value, because this is all going to be with respect to y, all the way up to the top y value, which is 2. All right, here we go. So I'm actually going to rewrite this first just because it makes me happier. So we've got negative y squared minus y plus 6, just a little bit of standard form, and now let's get to it. Antiderivative, negative 1/3 y cubed minus 1/2 y squared plus 6y from 0 to 2. Nice part is if you plug 0 into all these, they just go to 0, so I'm just going to do the 2 part, and that's going to be negative 1/3 of 2 cubed minus 1/2 times 2 squared plus 6 times 2. And I know this is going to turn into a fraction, so I'm going to be the ultimate lazy, or we'll big brain this if you want, and here is my answer. Yay, us. All right, now the fun one though. The region R is the base of a solid for each y, cross section, perpendicular, rectangle, base height is 2 times y. All right, an integral expression. So let's draw this first. It always helps me to give an idea of what's happening. Perpendicular to the y, here is my beautiful rectangle where we have the base down at the bottom, and we have a height which is a consistent twice whatever the y value is. Okay, so here we go. First things first, we need an area function. An area of a rectangle is always a base times a height. They give us that the height is 2y, and the base is right minus left. Go clever us, we already know right minus left here. The right function is 6 minus y, and the left function is y squared. So there's my area function. We could even clean that up a little bit and just lose those parentheses. 6 minus y squared times 2y. Great, area function. Volume, oh, I put a of x. This is a of y, isn't it? Because y is our independent variable now, plugging it in. So v of y is just the exact same thing. I'll rearrange like I did before just for my personal happiness, times dy, and that is, of course, giving this just a little bit of width here. Something like that. Yeah, not terrible. Okay, and then, of course, we need an integral. The integral is going to be our negative y squared minus y plus 6 times 2y all of that times dy to give it a third dimension, and then from where to where, same thing as before, 0 to 2. So by looking ahead quickly, we were able to save us some time and realize that although we could have done this one way, it made more sense to do a little extra work at the beginning, right minus left, and that actually simplifies our antiderivative a little bit too. We don't have to deal with the antiderivative of x to the 1/2. All right, last problem, the funnel problem. Ooh, this problem. This came out maybe 3 or 4 years ago, so maybe 2016, 2017, around there. And this was our most memed problem on Twitter directly after the AP exam. Students did not like this problem, which was funny because although there was a decent amount of calculus, the actual setup, which is what normally throws them off on these three-dimensional problems, was very easy. So let's see what we can do. First step, find the average value of the radius. Well, do we have a radius? Oh, we have an equation for a radius. That's cool. Average value of a function. Well, this radius is r of h, in case you were curious, because they're plugging an h value in. H is, of course, the height. So if I want to find the average value of a function, we have our average value theorem, average value formula. 1 over 10 minus 0, we're taking that from over here, right, times the integral from 0 to 10 of 1/20th 3 plus h squared dh. All right, well, let's simplify a bit. I have a 1/10th outside and a 1/20th. Let's bring the 1/20th out front. 20 times 10, that seems like 200. So I have 1/200th integral from 0 to 10 of 3 plus h squared dh. Antiderivative time. These antiderivatives aren't bad at all. 3 becomes 3h, h squared is 1/3 h cubed, and we're going from 0 to 10. Don't have to worry about plugging in 0 because that turns it all to 0. If we plug in 10, we're again going to be efficient. That's the nice way to say lazy here. And it becomes 3 times 10, that's 30, plus 1/3 times 10 cubed, and we're done. Great. There's the average value. Each one of these problems, if I remember correctly, was worth 3 points. So that's 3 points, and it took us 1 minute. Great. Out of the 15 total, we are doing wonderfully. Find the volume of the funnel. Well, this one is trickier, but they told us something. They told us that it has circular cross sections. So circular cross sections means if we cut this, we're going to see a cross section that is a circle, which should make sense. If you cut a funnel sideways like this and you open it up, you'll see a cross section that's a circle. Okay, so let's start with our area of a cross section, right? Our area of a cross section is, of course, it's a full circle. It's going to be pi r squared. I can do it like this. So if I wanted an area function, well, we're going to, if we think about this little width that I gave it right here, and we think of maybe this as an axis and this as an axis, this width is lying across the h-axis. So this width right here is dh. So that means everything in my formula needs to be in terms of h. A of h equals pi times the radius, but how do I change r to an h? Well, we have a formula that converts r to an h. 1/20th 3 plus h squared, and let's see, that's pi times the radius. Oh, but it's pi times the radius squared. There's my area formula. Area of a cross section, pi times the radius squared. Right? Our volume formula is the exact same thing, but I'm going to clean this up a little bit. Not too much yet, but I'm at least going to square the 1/20th. 20 times 20 is 400, I think, and then I'm going to move that out with the pi. So it's pi over 400 times 3 plus h squared squared times dh. There's my volume formula. And then we actually have to find the volume. So again, the tough part on this problem was actually doing a decent amount of calculus, a lot of antiderivatives, fundamental theorem. There was a lot there. But most of my students got really tripped up on the setup. And so I'm really trying to make sure we hit this a bunch before the AP exam. So we need to integrate this lovely piece. Now pi over 400, though, that's a constant. So let's put that outside of the integral. And we have 3 plus h squared squared dh from what to what? Well, they tell us, and this graph is not great this way, they tell us that the h's go from 0 to 10. So 0's down here, this has got to be 10 up here, so 0 to 10, those are both h's. Now, I could understand getting a little confused here of how do we take that antiderivative? Well, we can't do anything yet, but what we can remember is how to square something. That just means 3 plus h squared times itself, and I'll leave you to do the math, but I'm pretty sure it comes out to be h to the fourth plus 6h squared plus 9 dh. And now we have some fundamental theorem stuff going on. So pi over 400, fundamental theorem, 1/5 h to the fifth plus, that's a 6, this is going to be a 3, that's got to be a 2, I think, plus 9h from 0 to 10. And again, be efficient. 0 turns everything to 0, plug in 10, so I'm looking at pi over 400 times 1/5 10 to the fifth plus 2 times 10 cubed plus 9 times 10. And this is a great problem for you students that love to work out the final answer. You could do that, but that just sounds awful. So just be careful. I would stop right here. This is the volume of the funnel. All right, last part. We're whipping through this. Nice job. The funnel contains liquid that's draining from the bottom. So we have like drop, 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 and sad face. No one wants anything draining out. Okay, at the instant when the height of the liquid is h equal, I'm going to stop you right there. This is a related rates problem. At the instant, dead giveaway. Related rates. Let's set this up. We want the rate we know, the rate we want, the equation that links our variables together, the derivative of that equation, and don't forget that the derivative is always going to be with respect to t, and then we need to evaluate that derivative. Okay, so now let's get back to it. At the instant when the height of the liquid is h equals 3 inches, the radius of the surface of the liquid is decreasing at 1/5 inches per second. At this instant, what is the rate of change of the height of the liquid with respect to time? Man, I wouldn't even know where to start, except we have this cool setup. So what rate do we know? Well, rate of, oh, there's one. The radius of the surface of the liquid. So I'm just going to say that that's dr dt. The radius is changing, right, at a rate of 1/5 inches per second. But be careful, because it says decreasing. This rate would mean our radius is increasing. We need a negative. All right, well, what do we want then? What rate do we want? At this instant, what is the rate of change, there it is, of the height? So we want dh dt. And it's almost always going to be set up. We want dh dt when something happens. What else haven't I used here? Oh, when the height of the liquid is 3. So when h equals 3. All right, we need an equation. My equation has to link our two variables together, r and h. Don't worry about derivatives. Do we have an equation that relates r and h? Haha, we totally do. It's this one right here. R equals 1/20 times, and then I think it's just that 3 plus h squared, right? And actually, since I think we're going to have to take the derivative of this, I'm going to distribute the 1/20. I think it'll probably make our lives easier. So we're going to get r equals 3/20 plus 1/20 h squared. All right, derivative time. We need to take the derivative of each side, and we need to do it with respect to t, because they're talking about with respect to time here. So I need to take the derivative of r, and I need to take the derivative of the right side, 3/20 plus 1/20 h squared. ddt of r, well, I mean, if it really helps, think of it as r over 1 and air quotes multiply and air quotes straight across, dr dt. R is changing over time. Derivative of the right side, 3/20 is a constant, 1/20 is a constant, and I'm going to put this in parentheses right here. The 2 is going to come down in front. H stays the same to the first power, but then our chain rule says we have to multiply by the derivative of the inside, and the derivative of h with respect to time is dh dt. So let's clean this up a little bit. We have an equation, and my equation is dr dt equals 2/20 is going to be 1/10, I think. This is h times dh dt. All right, back to it. We know dr dt. That is going to be negative 1/5. Okay, we know it's when h is 3. That's very nice. And so we just need to isolate dH dt. Well, actually, it's probably easiest if we combine this fraction first, 3/10 times dH dt, right? And then just multiply by the reciprocal, so multiply both sides by 10 over 3. Okay, those are gone, and it tells us that dH dt is, well, we can go all together. Negative 10 over 15. That's probably a good enough place to stop. However, you could also reduce, divide by 5, negative 2/3, and then also you could remember your units, dH dt, right? Change of height with respect to time. The height is in inches, and the time is in seconds. So height is changing as time goes on in inches per second. And we're set. So yeah, a decent amount of setup here, but this is a really good problem. It brings everything together that we've done for the year. We have all of this done now. Make sure you turn this in on Teams. Thank you for your hard work in this tricky time. Please let me know if there's anything we can do for you or your families. Keep up the great work. I'm excited to see your success on the AP exam.